So next example that we're gonna cover is about linear arboricity of graph. So what is linear arboricity? When we say a linear forest, it is a forest which is a disjoint union of paths. And we say the linear arboricity LA of G is the minimum number of linear forest in G whose union is the set of all edges of G. So when we have a graph, we want to figure out its linear arboricity. The well-known conjecture regarding linear arboricity is this linear arboricity conjecture. Which says that the linear arboricity of a deregular graph is ceiling of d plus 1 over 2. If you consider, why would we have this number? Is that if we have a graph G, and if we decompose it into linear forest, then each linear forest has at most n minus 1 edges. So linear arboricity must be lower bounded by the number of edges divided by n minus 1. But if we have a deregular graph, the number of edges is tn over 2, n minus 1, and this is bigger than t over 2. So it lists it, because this is an integer, so this shows that this has to be at least this number. On the other hand, we know that any graph with maximum degree delta can be colored, each edge can be colored with delta plus 1 colors. So any deregular graph its edges can be decomposed into t plus 1 matchings. And if you have t plus 1 matchings, and if you pair each two of them together, then these two together forms a graph with maximum degree at most 2. So it's disjoint union of cycles and paths. Cycles and paths. So it's asking is that can we somehow, do a bit better than this? Can you make sure that we don't have any cycles? And every component of these are actually, paths. So that asks you, that's the motivation of this conjecture. And this lower bound is easy, but the upper bound is difficult. And alone in 1988 showed that for large D, we can find the upper bound, which is, let's write it this way, 1 plus little of 1 times D over 2, so which shows an asymptotic upper bound on this conjecture. And what we want to prove is the following, slightly better bound. For every D regular graph G, we have the linear arboricity of G is m mod D over 2 plus big O of D to D3 over 4 log square root of log D. So this is what we want to prove. And actually, I mean, in order to make some analysis easier, let's prove the directed version of this. We say the regular digraph is a digraph where every vertex has out degree D and in degree D. And we say linear directed forest is a disjoint union of directed paths. And we say the bilinear arboricity of a digraph G is the minimum number of linear directed forests in G, whose union covers all edges of G. Here you say whose union covers all edges of G, or you can say that the edge set of G partitions into, same number of directed forests. Both are equivalent. Because if you have a directed forest and all linear, directed linear forest, or undirected version, linear forest, if you delete some edges, then it is again linear forest or directed linear forest, linear directed forest. So conjecture regarding this bilinear arboricity is that for every D regular digraph D, we have this directed linear arboricity exactly D plus 1. So one notice is that if you have 2D regular graph, then it's every vertex has even degree, so you can find the Euler circuit. And by taking the Euler circuit, and then you move along the Euler circuit and then decide to how to orient each edges, then you get a D-regular digraph D. So if we know this, then this conjecture, then it implies this linear arboricity conjecture for even D. It's a straightforward implication. So we want to, I mean, give me a moment. Yeah, actually, yeah, we want to prove, I mean, this theorem in terms of a digraph. So if D is even, as I mentioned, we just prove for directed graph, then it is done. If D is not even, then, I mean, then still, I mean, we can actually, there are several ways to actually do it. So you take, say, for example, 2 copy of G and then add a perfect matching. Then this is D plus 1 regular graph G. And you take linear directed forest. You partition them into linear directed forest. And then you consider only the portion which has edges in here. Then again, I mean, you get a partition of this G into linear directed forest. And by this conversion, you might add 1, but here, the addition of this 1 is just observed in this term. So it's still okay. So we just want to focus on proving the similar statement for directed linear arboricity is bounded by this number. I mean, when, of course, you have to change this into D, when D regular digraph, we want to show that this is upper bound for bilinear arboricity. So how do we want to prove this? So somehow, as I mentioned before, if we want to just partition the edges into cycles and paths, then it is not difficult. But once we have the cycles, and one natural way is that we choose one edges from here, each other, and then we take that out. Then the remaining thing becomes all linear forest. But while doing that, we have to also cover these edges. So we collect this together and then hope that this forms again linear forest. Best scenario may be matching. So if these forms matching, then we take another one matching, which is a linear forest. Then we have several linear forests. And then possibly adding one more thing, we may be able to prove what we want. So here we have D many things, D many linear forests, and then one additional one comes from this matching. That's what we can, hope for. Of course, this is not, feasible. Otherwise, this would be not a conjecture, would be already proved. But if we have a certain more condition, we might be able to actually do this. So we need something like this. So this has a collection of edges. So let's say we have a set of edges. And set of edges. And set of edges, which are a collection of edges in this cycle. And we want to choose one edge here, and one edge here, one edge here, one edge here, so that these edges form matching. So instead, if we change this edge into a vertex in a line graph, Then in the line graph, we have a vertices, we have vertices, we have vertices, we have vertices. And then if this vertex is actually an edge here, edge here, edge here, if this edge and this edge are incident, then these are adjacent. So we have several sets. And then we choose one vertex from each set, and then we want to make sure that that's independent set. So that's roughly the kind of proposition that we want to prove. So actually we can do similar things. We can prove similar things using local lemma as long as each vi is large and then graph has bounded maximum degree. So this is a proposition that we will use later in this manner. So let H be a graph with, say, maximum degree D, and P of H is partitioned into R sets. The vertices are partitioned into R sets. And suppose each vi has size at least 2 times E times D. Again, E here is the natural, base of the natural log. Then we want to show that there exists an independent set W that contains a vertex from each vi. So let G be 2 times E times D and taking shilling of it. And as long as we can find the one W which is independent and then contains a vertex from each vi, it's okay. So that's what we want. So from each vi, we can delete the vertices if necessary. So we assume that each vi has size exactly G. So if it has more vertices, we just delete them. And among the remaining vertices, if we find an independent set in there, then that's again an independent set in the original graph. And which, if this W intersects with this vi after deletion, then it also intersects with the vi before deletion. So this we can assume. So for each I, we pick one vertex in vi independently, uniformly, at random. And let W be the set of chosen vertices. And now we show that with positive probability, W is actually an independent set. Then that shows that there exists a choice of W which is an independent set and intersects with each vi. So now let's consider the bad event. So what's the bad event? For each, say, HF, we don't write E because we don't want to confuse with the base of the natural log. We write AF with a bad event that both ends lies inside of W. So W contains both endpoints of F. Then what's the probability of AF, the bad event? You have VI and VJ. You have some HF. F, I mean, because each VI is a, no. So we choose one from here and one from here. So any H which lies inside of one VI is never chosen. So that's never included in, if we have a F here, then it's never included in W, so we don't have to worry. So we consider some F which lies in VI and VJ. Then in order F to be inside of W, in order this AF to happen, our chosen vertices from here must be here, and our one vertex chosen from here must be this, which happens with probability 1 over G square. Actually, this is an equality because we said that each set has a size G. But anyway, we have this inequality, which is enough. And we want to also count how many other AF prime, which these events are depends on. I mean, so we have this F in VI and VJ. So if F lies in VI union VJ, then this AF is actually mutually independent of all events AF prime, where AF prime does not intersect with this VI and VJ. Because again, by mutual independence principle, there are GI, GJ, GK, so which is a random variable which we choose one vertex from each VI, VJ, VK. They are independent, and this AF is depending on these two events. So any F prime which depending on G sub K, where K is not Gi, and G sub K prime, which is also not I or J. So these events, this AF is mutually independent of all such events. Thus, if you consider the dependency diagram, for the events AF, here, I mean, if there is an H inside of VI, then we are never gonna pick that. So we might as well just assume that each of VI is independent set, so that we can just write this. Otherwise, we can write that this intersection with VI is, smaller than 2 for any I. We can add this clause, but just for simplicity, let's just assume that all the edges of H are crossing between some VI and some VJ. So, dependency diagram for this has maximum degree actually smaller than 2 times G times maximum degree of H, because we have VI, VJ, we have this F, then what are the events that's not counted on here are, you just have to count the number of edges F prime which intersect with VI and VJ, VI or VJ. So you take the number of vertices here, which is 2G, and each vertex is incident with at most maximum degree of H many other edges. So this many, but this is strict because F is already counted in here, so we have to subtract 1. So if you exclude your own self, then you get this. Strictly smaller than that. This is 2GD So now what do we have to compute? The probability, the natural log, the natural base of log E times the probability of bad event, which is 1 over G square, and then D plus 1. Here D is actually the maximum degree of dependency graph plus 1. So maximum degree is strictly smaller than that, so you have to multiply this. And this is actually strictly smaller than 1 because this is what we get, and the upper one is never an integer, so this is strictly smaller than 1. So now we can actually robust local lemma implies that with positive probability, none of the events AF holds. This means there exists an independent set W which intersect all I. This completes the proof. So using this, now we want to do as we wanted. So for each this edge set, we want to choose one, so that the chosen edges, which corresponds to a vertex in this line graph, they are independent set, meaning that this forms matching. But there is one condition here, that each bi has to be large. So if all the cycles are long here, then we can do this. So using that, we can prove the following theorem, which says that the bilinear arboricity conjecture is true if the graph has large girth. Recall that girth is the size of shortest cycle. So we want to prove that the conjecture holds for graph with large girth. And then what we want to do is we want to prove, so recall what's our goal. Our goal is to prove this. And how do we want to prove this? We decompose this G into G1, G2, and G say S for some S, so that each one of them has large girth, with maybe some G0, which may not have a large girth, but most of them has large girth. And then we apply the theorem to here, so that so this is H partition. So you partition the H of G into several graphs, and all but one has a large girth. And for that, we partition the H's into directed linear forest. And this one, you do some other way, which will result in some error term here, because we have to deal with the last one. But that's roughly what we want to do. And for that, we have to show that the conjecture is true for graphs with large girth. And first, we have a D-regular digraph. Then we can use Hall theorem to decompose D into D distinct one regular spanning digraph F1 to FD. So this is typical trick. So you have a vertex set of D, and you take one copy of vertex set of D, and U, V. If you have a UV is a directed edge in D, then you put this here. Let's say this is B prime. So everything here is prime. Then you have this bipartite graph. And this bipartite graph, you have a deregular bipartite graph. So let's say B and U prime, you don't add in this direction. You add only, for each of them, you add in this way. So this has out degree and this has in degree. But you forget the direction. And here, if you find the perfect matching, then you get the corresponding edge here forms a one regular spanning digraph. So here you have a deregular bipartite graph, whose edge can be colored with D colors. So you decompose the edges into D perfect matchings, and each perfect matching corresponds to a one regular spanning digraph here. So that's typical way of applying Hall theorem to prove this. So that means, so what does it mean? So each one of them is one regular spanning digraph, meaning that every vertex has out degree 1, in degree 1. So it's actually disjoint union of cycles. So this, in other words, each of Fi is disjoint union of cycles. So this can be actually decomposed into, say, R many, edge set, where each E sub I forms a cycle. Moreover, because of the Gauss condition, the number of edges there is at least G, which is at least A times ET. And now we consider the line graph. So we all have learned what is line graph in undergraduate graph theory. Line graph has a vertex set. Vertex set of line graph is the edge set of the original graph. And edge set of line graph is collection of E and E prime, where E and E prime shares an vertex, and both of them are the edges of that. So for example, E1, E2, E3, then E1, E2, E3, you put the vertices and then you add an edge between two incident edges. So that's how you consider line graph. Anyway, you consider the line graph of the, say, underlying graph of D. Here, underlying graph of an digraph is you take all the edges and you forget the orientation. Then you get an undirected graph. That's called the underlying graph. And this is 4D minus 2 regular. It's not difficult to actually check. Give me a moment. Yeah. Because you have a one edge, then there are 2D minus 1 edges. Because this deregular digraph, that means every vertex has D outgoing edges and D incoming edges. So 2D edges in total. Here 2D minus 1. So in total, E is incident with 4D minus 2 other edges. As each EI has size at least 8 ED, which is at least 2E times the maximum degree of this line graph. The previous proposition implies that there exists a set W of edges of D which contains an edge of EI. for all I between 1 and R. And moreover, and this is an independent set in the line graph, which means it forms a matching of the underlying graph of G, underlying graph of T. So you consider M and you delete M from F1, you delete M from F2, and you delete M from Ft. These are T plus 1 directed linear forests. Which covers all edges of T. This shows that the directed linear, arboricity of G is at most T plus 1. And lower bound is, as we mentioned, it has T times number of vertices edges, and each directed forest has number of vertices minus 1 edges. So this is number of vertices. Then this is bigger than T. So it shows that this is exactly T plus 1. So now we have this theorem on our hand. What's left is we want to decompose the given directed graph, T-regular directed graph G. We want to decompose it into graphs with a high girth, and then we want to apply the previous theorem to each one of them. That's what we want to do. So in the next video, we will prove one more lemma, which roughly tells you how to decompose a graph into several graphs with high girth. And we also have to ensure that each graph with high girth that we decompose G into must be also somehow regular, or at least close to regular, so that we can actually apply this theorem. So in the next video, we prove one more lemma regarding that. And then using that lemma, we actually want to prove the statement we wanted.